In this lesson, I will talk about the graph of rational functions. Given two polynomial functions p of x and q of x, the rational function f of x takes this form, in which q of x is not equal to 0. The domain of this function is the set of real numbers except those values of x where q of x is equal to 0. These are examples of graphs of rational functions. And let us compare it with the graphs of polynomial functions. What is unique about the graph of rational functions? Well, what we can see here, what is strikingly unique about it is the presence of restrictions. Okay? So, for example, in this graph, your graph cannot intersect, okay, it cannot intersect this line. Or the graph, these two branches of the graph are not connected. Okay? They are not connected. They have a break. So what's striking about them is the presence of vertical asymptotes. Okay, so this one is the vertical asymptote of this function. Okay, and this is the line x is equal to 1. This one is a function whose vertical asymptote is the line x is equal to -1. Okay, so this one has two vertical asymptotes. This one is x is equal to 2. And this one is x is equal to -2. Okay? This one, not only does it have a vertical asymptote, it has an asymptote that is not vertical, okay, and not horizontal. This is an oblique asymptote. So an oblique asymptote is an asymptote that is slanted. It is a slant line. And this one has an equation. This one is the line y is equal to x plus 2. Now this one does not have a vertical asymptote. It does not have a horizontal asymptote nor an oblique asymptote, but it has a break. Okay? Again, the graph is not connected. So this part of the graph is not connected to this part of the graph. So when you see something like this in the graph of a function, that is an open circle. That is an open dot. That is not a part of the graph of your function. And you know why this graph came to be this way? Because we have restrictions on the domain of your rational function. Okay? So the domain of this function, for example, here, the domain of your rational function is, and so that is the reason why this graph came to be this way. We have restrictions on the domain of your rational function. But in other respects, the things that we see in polynomial functions, we also see it in rational functions. Just like with polynomial functions, our rational functions can have x-intercepts. Okay, so the x-intercept is the point where your graph intersects the x-axis. So this one, the x-intercept is x is equal to 1. Here, the x-intercepts are the points x is equal to -1 and x is equal to 1. But sometimes it happens that there are no x-intercepts. Here, for example, you have no x-intercept. And the same with this one. And the same with this one. Okay? Because that one, okay, is not part of the graph of your function. So given a rational function, the zeros of your rational function are the values of x such that p of x is equal to 0. Okay? So this one, okay, when we are interested to find what is the x-intercept of this function, let's say, for example, we are not given the graph. Judging from how we defined your rational function, what we shall do is we shall pay attention to the numerator. And when is that equal to 0? So that is 0 when x is equal to 1. Okay? So the x-intercept is this one. Let's say, for example, we are not given the graph. We are only given the equation that defines the rational function. If you wish to find out what is the x-intercept or what are the x-intercepts of this function, what you do is you pay attention to this, to the numerator, x squared minus 1. When is that equal to 0? And that is equal to 0 when x is equal to 1 or when x is equal to negative 1. So these are the zeros of your function. How about this one? F of x is equal to 1 over the square of x plus 1. So again, to find the zeros of your function or x-intercept, what you do is you focus on the numerator. When is it equal to 0? But this one is not equal to 0. It is a constant. It is equal to 1, which means that this rational function has no x-intercept. Okay? How about the vertical asymptote? So the vertical asymptote or the vertical asymptotes are or is x is equal to a when q of a is equal to 0. So this is a rational function that is in reduced form. So when your rational function is already in reduced form, to find the vertical asymptote, you pay attention to the function in the denominator. When is it equal to 0? So this one, for example, the vertical asymptotes are this one. So these two are the vertical asymptotes. And if we are not given the graph, we can obtain the vertical asymptote of this function from here. Okay, when is this equal to 0? And that is equal to 0 when x is equal to 2 or when x is equal to negative 2. This one, the vertical asymptote is x is equal to 2. So remember this. The line x is equal to a is a vertical asymptote of your function when, okay, look at this, because you will see this often in differential calculus. The line x is equal to a is a vertical asymptote if and only if. I think I should have written this as an if and only if statement. But this will also do. This will also do. The line x is equal to a is a vertical asymptote if and only if when x approaches a, okay, you will see this notation often when we go to limits. When x approaches a, y, okay, so the y coordinate of your graph approaches infinity or it approaches negative infinity. And that is what we are seeing here. Look at this. So when the values of x approaches 2, and you can do that in two ways. You can approach 2 from the right. You will see this often when we go to the topic of limits. So when you say approaching 2 from the right, x will take on values greater than 2, and you will get closer to 2. And what happens here is when x approaches 2 from the right, look at this, look at this. The graph of your function, and in particular the y-coordinate of the graph of your function, approaches infinity. And when x approaches 2 from the left, okay, so this is 2, the values of your x takes on values that are less than 2, your graph, or y, which is the value of your function, y approaches negative infinity. So whenever you see that kind of behavior in the graph in relation to a vertical line, that vertical line is a vertical asymptote. You will see these two notations often. Given a rational function in reduced form, the line y is equal to b is the horizontal asymptote if and only if y approaches b when x approaches infinity or when x approaches negative infinity. So here, when x approaches infinity, your function approaches the line y is equal to 0. Okay, so the horizontal axis, the equation of that line is this one, y is equal to 0. This one is a horizontal asymptote. This one, the horizontal asymptote of this function is the line y is equal to 1. When x approaches infinity, the value of your y or the value of your function approaches the value y is equal to 1. So this is the horizontal asymptote. Given a rational function, the line y is equal to mx plus b is an oblique asymptote if and only if our function approaches that line when x approaches infinity or when x approaches negative infinity. So this one has a vertical asymptote and an oblique asymptote. So the vertical asymptote came from this. This is equal to 0 when x is equal to 2. This one is the oblique asymptote, and the equation of this asymptote is equal to y is equal to x plus 2. The slope is 1 and the y-intercept is 2. Oblique asymptote arises when the degree of your numerator is greater than the degree of your denominator, and in particular when the degree of your numerator is greater than the degree of your denominator by 1. So this one is a degree 2 function. This one is a degree 1 function. So the difference is 1. So whenever you have that, whenever the difference between the degrees of your numerator and denominator is only 1, that will give way to an oblique asymptote. And if you want to see exactly what is the equation that will define the oblique asymptote, all you have to do is do this. Divide x squared minus 1 by x minus 2. And when you do that, you will get something like a quotient. Let's call that h of x plus a remainder. And h of x here is going to be a linear function because here the degree is 2. This one is a degree 1 polynomial. So when you get the quotient, it's going to be degree 1. You try it. You divide x squared minus 1 by x minus 2. And the quotient that you will get is y is equal to x plus 2. So this one has an oblique asymptote. The oblique asymptote of this function is the line y is equal to x. Oblique asymptotes arise whenever you have a rational function where the degree of your numerator is greater than the degree of your denominator by 1. So if you want to see exactly what is the equation of your oblique asymptote, what you do is you perform the division. So this is going to be equal to a quotient h of x plus a remainder. This is what will define your oblique asymptote. Rational functions without asymptotes arise when p of x and q of x have common factors, such as this one. Okay, so this one, your numerator is actually can be written in the form x minus 1 squared. So x minus 1 divided by x minus 1 will give you x minus 1. But x cannot be equal to 1. So you cannot just say that your function after reducing it is equal to x minus 1. No. You must append this restriction. F of x is equal to x minus 1 where x is not equal to 1. And this is the graph. This is the graph. So this one has no vertical asymptote. What it has is a break. This one is also a rational function. F of x is equal to x cubed plus x squared minus x minus 1. X plus 1 is actually a common factor. X plus 1 is a common factor. And when you divide it, when you divide x cubed plus x squared minus x minus 1 by x plus 1, this is the result, x squared minus 1. And so, to write this in reduced form, you must write it in this way. F of x is equal to x squared minus 1, but x is not equal to negative 1. Why so? Because our rational function is undefined. Our function is undefined when x is equal to negative 1. So how do you graph this? Okay, how do you graph this? You will graph it in the same way that you graph quadratic functions. But, okay, you must leave this open. You must leave this open. So this graph is not connected, okay? It has a break, okay? It is not continuous. Okay, so a word that you will hear about often later in our class. So this is how you graph it. It is the graph of a quadratic function, but this point is not part of the graph.